quiet archive record. Tonight, we pass into a world that asks nothing of you. No urgency, no weight, just the quiet unfolding of a story. In the middle of the 20th century, a few simple facts began to sit awkwardly together. The Milky Way is old, vast, and full of stars. Many of those stars are older than the Sun. Many should have planets. Given enough time, even slow processes can spread across a galaxy. Yet when we look outward, we do not see clear signs of other civilizations. No confirmed signals. No artifacts that everyone agrees are not natural. No visitors that can be proved. This mismatch between what seems possible and what we observe is called the Fermi paradox. It is not a single puzzle with one correct answer. It is a pressure test for our assumptions about life, intelligence, technology, and survival. Tonight, we explore the Fermi paradox and great filter theories. The story begins with a lunchtime remark that grew into a shorthand for a deeper unease. Enrico Fermi was a physicist who worked on nuclear reactions and the first controlled chain reaction. In 1950, during a conversation about UFO reports and space travel, he asked a question that others remembered as, "Where is everybody?" The exact words are not preserved as a transcript, but the idea is clear. If intelligent life is common, and if it develops technology that can cross interstellar distances, then the galaxy should show evidence of that. Even without faster than light travel, a civilization that builds ships that travel at a small fraction of the speed of light could, over millions of years, visit or settle large parts of the galaxy. Millions of years sounds large to humans, but it is small next to the age of the Milky Way. The paradox is not that we have not met aliens at a dinner table. The paradox is about absence at scale. If there are many technological societies, and if they last a long time, then at least one of them should have left a mark that we could notice. The mark could be a radio signal, a bright industrial signature in an atmosphere, a vast energy collecting structure, or a trail of probes. The exact form is uncertain, but the expected number of such marks, under many simple assumptions, is not close to zero. One way people try to make the problem concrete is by writing an estimate. The best known is the Drake equation. It is not a law of nature. It is a way to break a hard question into parts. In one common form, it multiplies several factors to estimate the number of active, communicating civilizations in the Milky Way right now. The factors include how often stars form, what fraction of stars have planets, how many planets might be habitable, how often life starts, how often life becomes intelligent, how often intelligence builds technology that can be detected, and how long such a civilization stays detectable. The Drake equation does not solve the paradox, but it shows where uncertainty lives. Some factors are now better measured than they once were. We know that planets are common. We have found thousands of exoplanets, and statistics suggest that most stars have them. We also know that small rocky planets are common, and that many exist in or near a region around their star where liquid water could exist on the surface, depending on atmosphere and geology. That does not mean those worlds are inhabited, but it removes one old excuse, which was that planets might be rare. Other factors remain almost unknown. The biggest unknown is still the origin of life. On Earth, life appeared early, perhaps within a few 100 million years, after the planet cooled enough for stable oceans. Some take that as evidence that life starts easily when conditions allow it. Others note that we have only one example, and we are forced to observe a world where life did start because we are here. That is an observation bias. We cannot treat our own existence as a random sample. Then there is the leap from simple life to complex life. On Earth, single-celled life existed for a very long time before large, complex organisms appeared. Multicellular life seems to have taken billions of years to develop. Intelligence capable of building radio telescopes arrived only near the end of Earth's history so far. If those steps are rare or difficult, then even a galaxy full of simple life could still have very few technological societies. The Fermi paradox becomes sharper when we consider colonization or expansion. A common argument is that once a society can build self-sustaining settlements on other planets or habitats, it can spread even if it moves slowly. The spread does not need a single government to plan it. It could happen as a chain. One settlement creates another. Over time, the frontier advances. Even if the frontier moves at 1% of the speed of light, the time to cross the galaxy is on the order of 10 million years. That is still much smaller than the age of the galaxy. If this spread happens even once, it could fill the galaxy with descendants, artifacts, or at least probes. So why do we not see them? One class of answers says the paradox is not real, because our expectations are wrong. Maybe travel between stars is much harder than we think. Maybe civilizations do not expand. Maybe their signals are hard to detect. Maybe they hide. Maybe we are early or we are late. Or maybe the galaxy is not full of life at all. Another class of answers uses the idea of a filter. The phrase great filter refers to a stage in the progression from dead matter to a galaxy-spanning civilization that is very hard to pass. If there is a filter, then most paths stop there. The filter could be behind us, meaning life or intelligence is extremely rare. Or it could be ahead of us, meaning many civilizations reach our stage, but then fail before they become long-lived and widespread. The filter framing is powerful because it forces a hard question. Which steps are easy and which are deadly? It also connects the cosmic question to human survival. If the great filter is in the future, then the silence of the sky may be a warning. To understand the filter idea, it helps to list the steps that might matter. First, you need a suitable environment. That means a stable energy source, complex chemistry, and long time spans. A planet like Earth provides this, but it is not the only possibility. Life might exist in subsurface oceans under ice, like those thought to exist on Europa or Enceladus. It might exist in clouds or in deep crustal environments. But we do not yet know which environments commonly allow life to begin. Second, life must start. That means a transition from chemistry to self-replicating systems that can evolve. We call this abiogenesis. We do not have a complete theory of how it happened on Earth. We have ideas, RNA as a first genetic system, metabolism first scenarios, and other pathways. But no lab experiment has produced a full living cell from scratch, and we have not found a clear prebiotic pathway that everyone agrees is likely. Third, early life must survive. Planets can be unstable in their youth. Impacts, volcanic episodes, and changing chemistry can sterilize or reset environments. Earth suffered heavy bombardment early on, yet life seems to have persisted or reappeared. If this early survival is hard, it could be a filter. Fourth, life must become complex. One key step on Earth was the rise of oxygen in the atmosphere. For a long time, Earth's atmosphere had very little oxygen. Then, photosynthetic organisms gradually changed the chemistry. Oxygen is reactive. It allowed high-energy metabolism, which supports large bodies and active behavior. But oxygen also causes damage. The transition may have involved mass extinctions and long periods of instability. If complex life depends on a narrow chemical window, that could be rare. Another key step was the origin of eukaryotic cells, which have internal structures like mitochondria. Eukaryotes are the basis for animals, plants, and fungi. The origin of eukaryotes may have required a rare event, an ancient merger between two cells that became an endosymbiotic partnership. If that merger is very unlikely, then complex life could be rare even if simple life is common. Fifth, complex life must build brains that can model the world and plan. Intelligence in this sense is not a single trait. Many animals show learning and problem solving, but technological intelligence, the kind that builds machines and radios, might require a specific mix of traits: dexterity, social learning, long lifespans, and stable environments. Sixth, technological intelligence must choose or be able to build tools that scale. It must access energy and materials. A civilization may need a path to fire, metallurgy, and industry. On Earth, humans had access to dry land, oxygen-rich air, and concentrated ores. A species in an ocean world might have difficulty smelting metals. It might still develop technology, but the path could be very different and possibly slower. Seventh, a technological civilization must last. It must avoid self-destruction, collapse, or permanent stagnation for long enough to become detectable or to spread. Longevity is a factor in the Drake equation. A civilization that emits radio for only a few hundred years is hard to catch. The Great Filter could be any one of these steps, or a combination. One early filter view says that life itself is rare. Perhaps abiogenesis is extremely unlikely. The chemistry may require a specific set of conditions that almost never align. Maybe Earth had a lucky sequence, a certain kind of ocean chemistry, a certain cycle of wet and dry environments, or a certain set of minerals that catalyzed key reactions. If that is true, then even if there are billions of habitable planets, only a few ever produce life. In that case, the silence is not surprising. This view feels plausible because we have not yet found life elsewhere. But we must be careful. We have barely looked. We have searched Mars with a limited set of missions. We have not drilled deep into Europa or Enceladus. We have not sampled exoplanet atmospheres at the level needed to detect subtle biosignatures across many targets. The absence of evidence is not strong evidence yet. Another early filter view says life is common, but complex life is rare. Microbes might be everywhere, but the jump to multicellularity and large animals might be a narrow bottleneck. On Earth, multicellular organisms evolved multiple times, but complex animals with organs and nervous systems may have required specific conditions: stable oxygen levels, plate tectonics, nutrient cycles, and long periods without global sterilization. The rare Earth hypothesis is a related idea. It claims that Earth has an unusual combination of features that support complex life: a large moon that stabilizes tilt, plate tectonics that recycle carbon, a magnetic field that shields the surface, a giant planet like Jupiter that reduces impacts, a location in the galaxy with fewer supernova threats, and a long-term stable climate. Some of these claims are debated. For example, Jupiter might also increase impacts by perturbing comets. The role of the moon is complex, but the broader point stands. Habitability may require more than being in the right temperature zone. A specific form of early filter focuses on eukaryogenesis, the origin of complex cells. Some biologists argue that this event happened only once on Earth and may be extremely rare. If so, then most planets with life may remain microbial forever. They might have simple ecosystems and maybe even stable biospheres, but they would not produce technological societies. Another filter candidate is the origin of intelligence like ours. Earth has had complex animals for hundreds of millions of years, yet only one lineage developed advanced language, abstract reasoning, and cumulative culture to the level needed for technology. Some argue that this suggests it is rare. Others argue that intelligence was trending upward in multiple lineages, and that if humans had not evolved, another species might have, given enough time. This debate matters because it affects whether the silence is expected. If the filter is behind us, it can make us feel special, and it reduces the sense of looming danger. But it also carries a different implication. If we are rare, we may be alone in a large region of space. That can change how we think about responsibility and the value of long-term survival. The late filter view says many civilizations reach our stage, but most do not persist long enough to fill the galaxy or leave clear traces. This can happen for many reasons. One late filter idea is self-destruction through war. Once a species gains control over large energy sources and destructive technology, it may face repeated risks of ending itself. On Earth, nuclear weapons created the first clear global self-destruction risk. Biological engineering creates another. Artificial intelligence could create more. The problem is not just a single event. It is the accumulation of risks over time. A civilization that lasts for 1 million years must survive many centuries where mistakes are possible. This connects to a simple point about probability. If there is a small chance each year of a catastrophe that ends the civilization, then over long times, the survival probability can drop to near zero. To become long-lived, a civilization may need strong stability, good governance, and robust safety systems. That may be rare. Another late filter idea is ecological collapse. A society might grow until it exceeds the limits of its planet, damaging climate, soils, oceans, and biodiversity. It could then collapse into a lower energy state that no longer emits strong signals. It might recover later, but the window of detectability might be short. If most societies go through a quick industrial surge and then crash, then the galaxy could be full of ruins rather than empires. A related idea is that technological civilizations may switch to low-leakage communication. Early radio broadcasts leak into space, but advanced communications might use tightly directed beams, fiber networks, or formats that do not radiate strongly. If so, then even if civilizations exist, we might not detect them with simple radio searches. This is sometimes called the Great Silence of SETI, the search for extraterrestrial intelligence. SETI has listened for narrowband radio signals for decades. It has not found a confirmed artificial signal, but SETI has searched only a tiny fraction of the possible signal space. Frequencies, sky locations, times, modulation methods, and directions. It is like dipping a cup into the ocean and not finding a fish. Still, The Fermi paradox is not only about radio, it is also about signs in the sky that might be easier to detect. For example, a civilization that captures a large fraction of a star's energy might build structures that re-radiate heat as infrared light. Such a structure is often called a Dyson sphere, though the realistic version might be a swarm of satellites rather than a solid shell. Astronomers have looked for strange infrared signatures. They have found some unusual objects, but none have become a widely accepted example of alien engineering. Another possible signature is industrial chemistry in exoplanet atmospheres. Certain gases, like chlorofluorocarbons, do not last long naturally, but could be produced by industry. Future telescopes might detect such signatures. At the moment, our measurements are not yet good enough for broad surveys. Then, there are artifacts in our own solar system. Some researchers propose that probes or relics could exist on the moon, in stable orbits, or in the asteroid belt. If an advanced civilization wanted to monitor many systems, it could send small probes. These probes could be quiet, powered by long-lived sources, and hard to detect. The absence of evidence here may simply be due to lack of thorough search. The probe idea leads to another set of theories. Perhaps the galaxy has been explored, but not in a way that makes itself obvious. One well-known proposal is the zoo hypothesis. It suggests that advanced civilizations might deliberately avoid contact with young civilizations like ours. They might observe, like scientists watching animals, and keep a distance. The motivation could be ethical, practical, or cultural. The problem with the zoo hypothesis is that it requires coordination among many independent civilizations, or at least a common policy that holds over long times. That seems hard, but it is not impossible. A single dominant civilization could enforce it, or there could be shared norms. Another related idea is the planetarium hypothesis, which is more extreme. It says that our observations are manipulated. We see a normal sky because someone makes it appear normal. This is hard to test and tends to move away from science into speculation. It is still sometimes discussed as a way to show how broad the space of explanations can be. A different set of theories suggests that contact is avoided, not for ethics, but for safety. This is often called the dark forest idea, inspired by science fiction. In a dark forest, every hunter stays quiet, because making noise attracts danger. A civilization that broadcasts could be noticed by a predator, so everyone stays silent or they hide their activity. For this to explain the silence, there must be real threats. One possible threat is a civilization that destroys other civilizations as a strategy. Another is a self-replicating weapon system that spreads and eliminates potential rivals. This leads to the concept of berserker probes, autonomous machines that seek out life-bearing planets and destroy emerging technology. Berserker scenarios are dramatic, but they highlight a point. Once self-replicating machines exist, they can spread quickly. A probe that can use local resources to make copies of itself is called a von Neumann probe. In theory, such probes could fill the galaxy in a short cosmic time. They could be used for exploration, mining, or even as weapons. If even one civilization launches such probes, we might expect to see them or their effects. So why do we not see them? Perhaps von Neumann probes are harder than imagined. Self-replication is complex. A probe would need advanced manufacturing, robust error correction, and the ability to handle unknown environments. But if a civilization is very advanced, it may solve these problems. Another possibility is that advanced civilizations choose not to build self-replicating probes because they are risky. A replicator could become a runaway system, consuming resources and behaving like a plague. A wise civilization might ban them. This becomes another filter. A civilization must develop restraint and control. There is also a possibility that we are early. The galaxy is old, but perhaps the conditions for life and technology become favorable only after a certain time. For example, heavy elements like carbon, oxygen, and iron are made in stars and spread by supernovae. Early in the galaxy, there were fewer heavy elements. Maybe Earth-like planets were rarer. Maybe life needs a certain metallicity, a certain abundance of elements. There are also cosmic hazards that were more common in the past, such as gamma-ray bursts. A gamma-ray burst nearby could sterilize large regions of a galaxy by stripping atmospheres or irradiating surfaces. If such events were frequent, they could reset the clock on evolution. Over time, as the rate drops, life might finally have long, stable periods to evolve. In that case, many civilizations might be roughly the same age, and the first galaxy-spanning ones might still be in the future. This is sometimes called a phase transition model. In the early galaxy, conditions prevent long-lived civilizations. Then at some point, the environment becomes safer, and many civilizations can arise. That could explain why we do not see ancient empires. It would also imply that in the next few million years, the galaxy could become more crowded with advanced societies. Another timing idea is that civilizations have short windows, and they are not synchronized. If the typical detectable phase lasts only a few hundred years, then even if many civilizations exist over the galaxy's history, only a few might exist at the same time. We could simply be missing them in time. This is a simple way to weaken the paradox, but the colonization argument pushes back. Even if a civilization is detectable for a short time by radio, it could still launch probes or settlements that persist. Those artifacts could last much longer. So the paradox remains if expansion is common. This leads to the question, do civilizations actually expand? It is easy to assume that growth is natural and inevitable, because humans have expanded across Earth. But that was on a planet with open land and accessible resources. Interstellar travel is different. The cost is enormous. The timescales are long. The benefits are uncertain. A civilization might decide that building local habitats, virtual worlds, or deep oceans of computation is better than sending ships to other stars. If advanced societies become very efficient, they may be able to satisfy most goals with local resources. They might focus inward on art, science, or simulated experiences. From our point of view, such a society would be quiet. Another reason expansion may be limited is that biology may not adapt well to space. Long-term radiation, microgravity, and isolation are severe. A society might still expand using machines rather than living bodies. But then the question shifts. Do machines expand? And if so, do they leave visible traces? A related idea is that expansion is possible but undesirable because it increases risk. Spreading across stars could create more places where accidents occur, including the release of dangerous self-replicators or conflicts. A civilization might adopt a policy of staying compact to reduce existential risk. These social and strategic explanations are hard to test because they depend on unknown alien values, but they are part of the full space of answers. Now we return to the great filter framework. One strength of the framework is that it connects evidence to our expectations about the future. If we discover that simple life is common, such as microbial life on Mars or Europa, then the early steps like abiogenesis might not be the main filter. That would shift the likely filter toward later steps, like complex life, intelligence, or survival. If we discover complex life, like multicellular organisms on another world, that would suggest that the path to complexity is not extremely rare. That would push the filter even further forward toward technological survival. In that case, the silence would look more like a warning, because it would suggest many civilizations reach our stage but do not last. On the other hand, if we search widely and find no sign of life anywhere, that would suggest that the early steps are rare and the filter is behind us. This is why the search for simple life is not just curiosity. It is a way to estimate where the filter might be. Another key concept is selection effects. We should not assume we are typical. We live on a planet where life started, survived, became complex, and produced a civilization. Any observer will, by definition, be on such a planet. This can bias our intuition. It can make rare events look common. For example, if abiogenesis is extremely rare, then almost all observers will still see that life appeared early on their planet, because if it appeared late, there would not be enough time for observers to evolve. So the early appearance of life on Earth does not prove that life is easy. It is consistent with both easy and hard scenarios. Similarly, we might be on a planet that avoided major disasters for long enough. That could be rare. The fact that we are here does not reveal how common such long, stable windows are. The filter model can be described in a simple way. Imagine many planets. On each planet, there is a chain of steps. Each step has a probability of being passed. The overall probability is the product. If one step is extremely low, it dominates. That step is the great filter. Now we can look at specific filter candidates in more detail. Abiogenesis as a filter has several arguments in its favor. First, we do not have a complete explanation. Second, the jump from chemistry to life is not trivial. Life requires information storage, replication, and metabolism. It requires membranes, gradients, and control. Third, in lab studies, organic molecules can form under many conditions, but they do not automatically assemble into living systems. Against this, we can note that Earth produced life relatively quickly after it became habitable. If the process were extremely unlikely, we might expect it to take a long time. But again, this is selection bias. Another early filter candidate is the origin of a stable genetic system. Some propose that RNA, which can both store information and catalyze reactions, could have been an early step. But RNA is fragile. It breaks down. It requires certain conditions. Perhaps the pathway to stable heredity is rare. Another candidate is the development of photosynthesis. On Earth, oxygenic photosynthesis changed the planet, but photosynthesis itself is complex. It uses pigments, electron transport chains, and specialized proteins. If photosynthesis is rare, then planets could remain with low-energy biological systems, limiting complexity. Then there is the oxygenation step. Even with photosynthesis, oxygen must accumulate. That depends on sinks, like iron in oceans and volcanic gases. It may require a balance. If oxygenation rarely occurs, complex animals might be rare. Eukaryotic cells are another strong candidate. The endosymbiotic event that led to mitochondria may have been a near singular accident. If eukaryotes are rare, then complex multicellular life is likely rare. Sexual reproduction is another step that can increase diversity and speed evolution. Some think it could be important for complex life, but sex is not the only way to exchange genes. Microbes use horizontal gene transfer. The importance is uncertain. Multicellularity appears to have evolved multiple times, which might suggest it is not a huge barrier. But the kind of multicellularity that produces large, complex organisms with specialized tissues might still be rare. Tool-using intelligence is another debated step. Humans have a combination of traits: upright posture, free hands, fine motor control, vocal communication, and a social structure that supports teaching and shared knowledge. These might not often align. Then there is cultural evolution. Human technology is not just individual intelligence, it is cumulative culture. Knowledge accumulates across generations. This requires stable social learning, language, and enough population and connectivity to keep skills from being lost. Some isolated human groups lost certain technologies over time. That shows that culture can regress. A planet with harsh, repeated disruptions could prevent long-term accumulation. Assuming a technological civilization emerges, the next filter is the transition to high-energy industry. Humans used fossil fuels, which are concentrated energy sources. Without them, industrialization might still be possible using biomass, wind, water, and solar, but it could be slower or limited. Some argue that a civilization might need access to concentrated fuels to reach space. But even if fossil fuels are rare, a civilization could mine geothermal energy or build large solar systems. The energy source matters, but it may not be a hard filter. A different kind of filter is the tendency for intelligence to be unstable. A species might develop intelligence as a tool for survival, but intelligence can also create problems. Overconfidence, conflict, and the ability to change the environment faster than it can be understood. A species might reach a point where it can cause global harm, but does not yet have strong institutions to control itself. This is sometimes called the vulnerable window. It is the period when a civilization has powerful technology, but has not yet learned to manage it safely. If the vulnerable window is long and the risks are high, then many civilizations may fail during it. On Earth, this window might have begun with industrialization and the development of weapons of mass destruction. It may continue with biotech, nanotech, and AI. A key question is whether the window can be crossed reliably. Another late filter is the possibility of irreversible stagnation. A civilization might survive but stop expanding and stop producing detectable signals. It might become stable, low growth, and quiet. It might live in virtual environments with minimal external footprint. In that case, the galaxy could contain many civilizations that are effectively invisible. Yet invisibility has limits. Even efficient systems produce waste heat. A civilization that uses enormous energy should radiate heat. If the galaxy had many very large energy-using civilizations, we might detect an excess of infrared emission. Since we do not see that clearly, either such civilizations are rare, or they are modest in energy use, or they use physics we do not understand. At this point, it helps to separate three questions. First, how many technological civilizations exist or have existed. Second, how many of them expand in a way that produces obvious galaxy-scale signatures. Third, how detectable are they to us with our current instruments? A civilization could exist and be non-expansionist and quiet. Many such civilizations could exist and still be hard to detect. But the Fermi paradox focuses on the expectation that at least one civilization would be expansionist and long-lived. Even if most are quiet, a single outlier could fill the galaxy. So the paradox is about tales of distributions. It is about whether the probability of an expansionist civilization is low enough that none have done it so far. One way to reduce the paradox is to argue that expansionist behavior is not stable. Suppose a civilization expands. It spreads across many systems. Over time, its colonies diverge. Coordination becomes difficult. Conflicts may arise. The civilization could fracture into many smaller groups. Some might become quiet. Some might die out. The result might be a patchy galaxy where no single civilization dominates and where visible signatures are limited. But even fractured expansion could leave artifacts. The question is whether those artifacts would be obvious. Another approach is to question the colonization timescale. The naive estimate assumes a steady wave of expansion, but real expansion could be slower. It could be limited by economics, by psychology, by politics, by biology, or by physics. Interstellar travel requires large energy and long-term reliability. Ships must survive for decades, centuries, or more. They must shield against radiation and dust. They must navigate accurately. The cost could be so high that few societies attempt it. Even if travel is possible, settlement is hard. Planets are not welcoming. Most worlds will require life support. Building self-sustaining ecosystems is difficult. A civilization might prefer building space habitats in its own system, using local asteroids rather than traveling to another star. If most advanced civilizations become space-based in their own system, they might still emit signatures, but perhaps their signatures are subtle, especially if they optimize for efficiency. Now we consider specific named explanations often discussed in Fermi paradox debates. The first is the idea of rare earth, already mentioned. It has many sub-claims: that stable climates require plate tectonics, that plate tectonics require a certain planet size and internal heat, that a large moon stabilizes axial tilt, that gas giants reduce impacts, that a quiet galactic neighborhood is needed, and that a planet must avoid nearby supernova. Some of these are plausible, some are contested. For example, plate tectonics may not be required for carbon cycling if other mechanisms exist. Large moons may not be required for tilt stability depending on other factors, and impact rates are complex. But the key idea is that complex life might require a long list of conditions, and the intersection of those conditions might be rare. The second is the idea of the Great Silence as a sign of a late filter. In this view, many civilizations arise, but few last. The silence is a symmetry. This is a grim interpretation, but it is logically possible. The third is the idea of the zoo and dark forest, which focus on behavior and strategy. The fourth is the idea that we are not listening properly. SETI might be looking in the wrong way. Aliens might use different frequencies, different coding, or different media. They might use neutrinos, lasers, or quantum communication. They might also communicate primarily within their own systems. Laser SETI searches look for brief flashes of light. Some surveys have been done, but the parameter space is huge. The fifth is the idea that we have not looked in the right place for artifacts. A civilization could build probes or beacons in stable locations, like Trojan asteroid points or the far side of the moon. These could be small and dark. We have not done a full survey at the needed resolution. The sixth is the idea that advanced civilizations might live in the outer parts of galaxies or in intergalactic space, where resources like hydrogen are abundant and where they can avoid hazards, or they might cluster around certain star types. Another important factor is star type. Red dwarf stars are the most common. They live for trillions of years. They have habitable zones close in, but they are also active when young, with flares that could strip atmospheres. Planets close in may be tidally locked, with one side facing the star. That could still be habitable with atmosphere and oceans, but it is different. If red dwarfs are less friendly to life, then perhaps Earth-like life is rarer than simple planet counts suggest. On the other hand, if red dwarfs are fine, then there could be huge numbers of habitable worlds. Now we examine the great filter idea with a simple mental model. Imagine 1 million Earth-like planets. Suppose half of them remain habitable for billions of years. Suppose life starts on 1%. That gives 10,000 worlds with life. Suppose complex life evolves on 1% of those. That gives 100 worlds with complex life. Suppose technological intelligence evolves on 1% of those. That gives 1 world. In that model, we are alone in 1 million, and the silence is not surprising. But if life starts on 50%, complex life on 10%, intelligence on 10%, then the numbers become large. Then we should expect many civilizations. In that case, the silence pushes us to assume that either civilizations are short-lived, or expansion is rare, or detectability is low. Because we have so little data, people can choose assumptions that fit almost any outcome. The value of the discussion is not that it yields a final answer today. The value is that it highlights what discoveries would matter. One discovery would be a second example of life in our solar system. If we found independent life on Mars, Europa, or Enceladus, that would strongly suggest that life starts easily given the right conditions. That would move the filter forward. Another discovery would be biosignatures in exoplanet atmospheres. If many Earth-like planets show oxygen, methane, or other chemical disequilibria that suggest biology, that would imply life is common. Another discovery would be a technosignature. Even one clear artificial signal or artifact would change the debate. It would prove that we are not alone. Now we turn to great filter theories in more detail, especially those that focus on future risks. A major modern candidate is artificial intelligence. The concern is not that AI is evil by nature, but that an advanced system could pursue goals in ways that conflict with human survival, if those goals are not aligned with human values. If a civilization builds systems more capable than its own members, and if control is not solved, then it could lose control of critical infrastructure, weapons, or resource allocation. This kind of risk scales. A small misalignment could lead to large consequences if the system is powerful. The risk could come quickly, because digital systems can improve rapidly. Another candidate is biotechnology. Once a civilization can design pathogens, it may create risks that are hard to contain. Natural pandemics can already cause severe harm. Engineered ones could be worse. A civilization that continues for centuries must manage repeated biorisks. Nanotechnology is another feared category. In extreme scenarios, self-replicating nanomachines could consume large portions of the biosphere. This is sometimes called grey goo. Many experts think this particular scenario is unlikely, but the broader point is that small-scale manufacturing and replication can create powerful risks. Then there is the basic risk of war with advanced weapons. Nuclear weapons are one example. Future weapons could include hypersonic delivery, autonomous systems, and cyber attacks on critical systems. Escalation could become faster than decision-making. There is also the risk of climate and ecological damage. A civilization that uses fossil fuels can destabilize climate. But even with clean energy, land use and resource extraction can damage ecosystems. Some collapse models suggest that complex societies can fall if energy returns decline, if inequality rises, or if environmental conditions degrade. The Great Filter does not have to be one event. It can be a long period where risks accumulate. A civilization that survives this period may reach a stable state with robust institutions and safety culture. It may then last for a very long time. If so, the distribution of lifetimes could be heavy-tailed. Many short-lived societies, a few long-lived ones. In such a distribution, the long-lived ones matter most for cosmic visibility because they have time to expand and to build large structures. If we do not see them, perhaps even the long-lived tail is rare. A further twist is that expansion itself could be the filter. A civilization might survive locally, but be unable to expand because expansion creates new risks and conflicts, or because physics makes interstellar travel too costly. In that case, civilizations could exist but remain isolated, each in its own star system. If that is the case, then the galaxy could be full of quiet islands. We might have neighbors, but we would not notice them. Another late filter candidate is resource exhaustion. A civilization might rely on a specific resource, like fossil fuels, for industrial takeoff. If that resource is limited, it might not reach space. But this seems less like a universal filter, because there are multiple energy paths. A more plausible resource-related filter is access to certain metals and minerals needed for electronics and industry. If a planet lacks accessible deposits, industrialization could be difficult. But again, advanced chemistry could find alternatives. Now consider the possibility that we are being watched. This is sometimes suggested in the context of the zoo hypothesis, and also in modern discussions about probes. The argument is that it is easier to send small probes than big ships. Probes can be cheap relative to moving whole populations. If probes are common, then our solar system could have been visited without our knowledge. A probe could hide in the asteroid belt, in a stable orbit, or even on the moon. It could have been here for millions of years. This idea is hard to rule out, but it is also hard to confirm. The practical question is, what would we look for? We could search for unnatural objects in stable orbits. We could map the moon at high resolution and look for shapes inconsistent with geology. We could analyze unusual asteroids, but the search space is large. Another important set of explanations uses the idea that our assumptions about alien technology are too human. Perhaps civilizations use technologies that do not create obvious signatures. Perhaps they use energy sources that do not produce much waste heat, or they manipulate matter in ways we would not recognize. However, Physics sets constraints. Any process that uses energy and creates entropy must produce waste heat somewhere, unless it exports it. A civilization could radiate heat at very low temperature to reduce detectability, but that would require large radiating surfaces. It could also hide by radiating heat in directions we do not observe. These are possible, but they add complexity. Now we consider a different family of explanations. The idea that the galaxy is not friendly to long-lived civilizations. In this view, the Great Filter is not internal self-destruction, but external hazards. One hazard is nearby supernovae. A supernova close to a planet can bathe it in radiation and cosmic rays. It can damage ozone and raise mutation rates. It can cause climate impacts. Another hazard is gamma-ray bursts, which can be even more intense. If such events occur frequently enough, they can reset complex life across large regions. Another hazard is asteroid impacts. Large impacts can cause mass extinctions. Earth has had several. The dinosaur extinction 66 million years ago was likely caused by an impact. If impacts are more common on many planets, they could prevent long, stable periods needed for intelligence. Another hazard is stellar variability. Some stars flare and emit strong radiation. Planets close to red dwarfs may be exposed to frequent flares, especially early on. If atmospheres are stripped, surfaces may be sterilized. These hazards could act as filters. Yet Earth survived many hazards. That again raises the question of how typical Earth is. Now we look at the paradox from a more statistical point of view. If you assume that civilizations exist, you might ask, how far away is the nearest one? The answer depends on the number density of civilizations and their lifetime. If there are only a few in the whole galaxy at any one time, then the nearest could be thousands of light years away. Communication would be slow, contact would be hard. If there are many, then some should be close. We should have seen signals. So again, the key unknown is how many exist and how long they last. The Great Filter idea suggests that one or more steps have probabilities so low that the overall number of civilizations is small. But it also suggests a more personal question. If the filter is ahead, what should we do? From a practical perspective, the answer is to reduce existential risks. That includes preventing nuclear war, managing biotech safety, aligning advanced AI systems, and maintaining stable environmental conditions. It also includes building resilient institutions and a culture that takes long-term survival seriously. It is notable that many of these actions are good for us, even if the Fermi paradox has a different explanation. Reducing global risks is valuable regardless. Some people argue that space colonization is itself a way to reduce risk. If humans spread to multiple planets or habitats, then a disaster on one world would not end the species. In that view, becoming multi-planetary is a way to pass a late filter. Others argue that expansion can increase risk by creating new points of failure and conflict. The best approach might be to first build a stable, safe civilization on Earth, then expand carefully. Now we return to the question of detectability. Even if civilizations exist, we might not notice them because we are looking in a limited way. We have only recently begun to search for exoplanets. We have only recently begun to measure exoplanet atmospheres. We have only scanned a small fraction of the radio sky. We have not built dedicated surveys for many technosignatures. Also, our instruments are limited. If an alien civilization is far away, its signals may be weak. If it uses narrow beams, we might miss them unless the beam hits us. Another point is that our own radio leakage has decreased in some ways. We use cable, fiber, and directed signals. Our most powerful transmissions are radar and certain communication systems. Over time, Earth could become less detectable. If other civilizations follow similar trends, the window of strong leakage might be short. Still, the paradox remains for expansion. A galaxy-spanning civilization might not broadcast, but its engineering could still be visible. So perhaps expansion is rare. One way expansion could be rare is if the first steps to interstellar travel are much harder than imagined. Even if you can build a ship that can reach another star, the travel time might be centuries. That requires a generation ship, suspended animation, or robotic explorers. Generation ships raise social questions. Can a small population remain stable for centuries? Can it maintain knowledge and health? Will it choose to continue the mission? These are real issues. Robotic probes avoid some issues, but they raise others. They require very high reliability and autonomy. They must repair themselves. Another issue is dust. At high speeds, tiny particles become dangerous. Shielding becomes heavy. Yet none of these seems absolutely impossible with advanced technology. Another way expansion could be rare is if the motivation is not strong. A civilization might decide that the best place to live is near its home star, where it has control and history. In that case, the galaxy could remain mostly empty of visible engineering. Now consider the scenario where there is one or more expansionist civilizations, but they are so far away that their expansion wave has not reached us yet. This is possible if expansion is not uniform, or if it started recently. If the galaxy has only a small number of expansionist civilizations, they might occupy separate regions. We could be in an empty region. This leads to percolation models, where expansion fills space in patches rather than as a single wave. In such models, some regions are colonized, some are not, depending on the distribution of habitable systems and the choices of colonizers. If percolation is real, then the fact that our system is not colonized does not mean no one is out there. It could mean we are in a gap. But percolation still expects some nearby colonized regions if the density is high. Now we move to a key emotional aspect of the Fermi paradox. The paradox is unsettling because it forces us to face two uncomfortable possibilities. First, we may be rare. The universe might be mostly empty of minds. Second, if minds are common, then something might be wiping them out or limiting them. Neither is comforting. Yet the paradox is also a scientific opportunity. It points to tests. For example, we can search for microbial life in our solar system. Mars remains a prime target. It once had liquid water on the surface. It has subsurface ice. If life ever emerged there, some traces might remain. Europa and Enceladus are also prime targets. They likely have subsurface oceans in contact with rock, which can provide chemical energy. Enceladus even vents material into space. We can sample those plumes. If we find life there, it would be a huge clue. Another test is to look for biosignatures on exoplanets, especially around nearby stars. This requires large telescopes and careful interpretation. Oxygen can be produced abiotically in some cases. Methane can also have non-biological sources. The strongest evidence would be a mix of gases that are hard to maintain without life. We can also search for technosignatures beyond radio. This includes unusual light curves from transiting objects, narrow laser pulses, infrared excess, and unusual chemical pollutants. We can search for anomalies in our solar system, though this is hard. The Fermi paradox also intersects with philosophy. If we are alone, then human culture, knowledge, and art might be among the only such things in our region of the universe that can give weight to preserving them. If we are not alone, then the universe contains other stories, other histories, and other minds. That can change how we see ourselves. But the great filter lens keeps returning to survival. If most civilizations fail, then passing the filter may require specific traits: restraint, cooperation, long-term thinking, and robust safety systems. We can think of the filter as an engineering and governance problem. Now, we consider a subtle point. The absence of evidence may not be uniform. The galaxy has regions. It has spiral arms, a central bulge, and a halo. The density of stars varies. The rate of hazards varies. The region where the sun sits is sometimes considered part of a galactic habitable zone, where metallicity is high enough for planets, but hazard rates are not too high. If this concept is correct, then life could be concentrated in certain regions. If civilizations are concentrated in certain regions, our search strategies should focus there. Also, if civilizations are rare, then we should focus on nearby stars and the closest potentially habitable planets. Now we consider the possibility that what we call the paradox is partly created by human expectations. Humans have stories about explorers and empires. We assume that advanced life would expand like a human empire. But alien life might not have the same drives. It might not value expansion. It might also be constrained by social structure. A species might be solitary. It might not build large cooperative societies. Or it might be highly cooperative and stable but content. In that case, the galaxy could be full of quiet civilizations. However, even quiet civilizations might send probes for science. Science seems like a strong, universal motive if minds are curious. But that is still an assumption. Another possibility is that civilizations quickly merge into machine intelligence and then migrate to environments better for computation, like cold outer regions where waste heat can be radiated more efficiently. A computing system benefits from cold temperatures because it can do more operations per unit energy, depending on constraints. If this is true, then advanced civilizations might cluster far from bright stars, and their signatures might be faint. Yet again, this becomes hard to test. Now we return to our own future. The Fermi paradox is not just about aliens. It is about what kind of civilization we are. If the great filter is ahead, then the most important era in our history may be this one. When we create technologies that can change the planet and ourselves. If we manage this era well, we could become a long-lived civilization. If we do not, we may become another silent statistic. This framing can sound dramatic, but it is grounded in the simple logic of risk over time. Now we look at common misconceptions. One misconception is that the paradox assumes faster than light travel. It does not. It only needs slow travel plus long time. Another misconception is that the paradox assumes aliens would visit Earth. They might not. The paradox is about evidence at a large scale. Another misconception is that the lack of UFO evidence proves there are no aliens. UFO reports are not strong evidence either way. The Fermi paradox is best approached with astronomy and biology, not with anecdote. Another misconception is that we have done a thorough search. We have not. Now we end by returning to the key choices. The Fermi paradox asks why the sky looks quiet. Great filter theories try to explain that quiet by placing a hard barrier somewhere on the path from chemistry to galaxies. We do not yet know where that barrier is, but we can see which discoveries will move it. Finding simple life elsewhere would move it forward. Finding complex life elsewhere would move it further forward. Finding a technological signal would confirm that the path can be passed at least twice. Finding nothing after deep search would suggest that Earth is a rare gift. Until then, the paradox remains a mirror. It reflects our ignorance about life. It also reflects our choices about survival. There is one more angle that often gets overlooked, and it is about scale. When people picture an advanced civilization, they often picture a single unified actor. But over long times, even a stable society might not stay unified. It might become a family of cultures, each with its own priorities. Some might explore, some might stay home, some might turn off their outward signals. The result could be a galaxy with activity, but without a single loud footprint that stands out. There is also the possibility that the most common form of intelligence is not like ours. It could be slow, distributed, and patient. It might live in oceans, under ice, or inside porous rock. It might not build radios. It might be intelligent in a way that never leads to industry. If that is true, then the galaxy could be full of minds and still look silent to our instruments. In other words, the paradox is partly a question about what we mean by intelligence and technology. Humans measure detectability by human outputs. We look for beams, factories, and big energy use, but nature can build complex systems that leave little obvious trace at long distance. Still, we can set some firm targets. The next decades will give us better data. We will measure more exoplanet atmospheres. We will map more nearby worlds. We will improve surveys for unusual infrared sources. We will keep listening for signals. Each new dataset will remove some assumptions and force the debate to move. If we ever find a second Genesis, a life form that clearly did not come from Earth, it will be a major shift. It will say that life is not a one-off. It will make it harder to place the great filter at the first step. It will push us to look harder at later steps, especially long-term survival. If we never find even microbial life after deep searches, then the opposite lesson will grow stronger. The first step may be the hardest. The universe may have many habitats that look friendly, but almost none that become alive. Either outcome matters for how we see our own future. If the filter is behind us, then the main task is to stay alive and avoid needless collapse. If the filter is ahead, then the main task is to learn how to handle power without losing control. The Fermi paradox does not tell us which path is true, but it gives a reason to treat the question seriously. The sky is a dataset. Silence is a clue, even if it is not yet an answer. There is also a pragmatic middle ground. The great filter might not be one wall. It might be many smaller hurdles that add up. Life may start on many worlds, but most biospheres may stay simple. Some worlds may reach complex life, but only rarely reach tool-making species. Some may reach tools, but fail to reach stable industry. Some may reach industry, but fail to avoid repeated self-made crises. Each small probability reduces the final count. This layered view fits what we see on Earth. Evolution is not a straight march. It is a messy process with dead ends and extinctions. Complexity can rise, then crash. Intelligence can appear in a limited form, then disappear. If that pattern is common, then a galaxy can have many experiments and still have few long-lived outcomes. When you look at the night sky, the most honest position is still uncertainty. But the structure of the uncertainty is clear. The silence points either to rarity, to short lifetimes, to hidden behavior, or to some mix of all three. And in every case, it makes the survival of a technological civilization a special and fragile thing. If there is a lesson that does not depend on the answer, it is that knowledge matters. The more we learn about planets, chemistry, biology, and risk, the less we will rely on guesses. The paradox will shrink, not because it disappears, but because each unknown becomes a measured factor. And until we have that data, the quiet sky remains one of the strangest results in science, a simple observation that keeps forcing deeper questions. This was a quiet archive story, where the story ends, sleep begins.